Welcome to another tutorial in plain English. In this video, I'll be demonstrating some of the tools available for MSYS MinGW for doing low-level programming. I'm running a fresh install of Windows 10. So, for those of you not fully versed in computer terminology, what exactly is a bootloader and why in the world should that be important to anybody else in the world besides me? Okay, you got your basic computer, right? And it's got a bunch of memory in it. And Windows can take up a lot of that memory. They recommend like 4 gigabytes of RAM just to run Windows, right? And then it kind of decides what to do with the remaining memory to run your various applications and such. However, when you're doing boot level programming, your program and your program alone is all that's running on your computer. So now that gives you full access to the dedicated resources of your computer. So what you would normally think of as a slow computer by today's standards can actually be quite sizzling fast when it's running a dedicated application, right? Now, then along comes Windows 11, and unfortunately, it just does not run on a lot of older computers. So now with them withdrawing support for Windows 10 and such, that could potentially mean hundreds of millions of computers that are destined for the trash heap. I don't know if you've ever seen the pilot episode of Max Headroom, where people are scrounging through electronic waste and finding old computers and making them work as a matter of survival. Yeah. Well, like today's modern times, I see like Microsoft and big companies pushing to get everybody to toss out their old computers and buy these new AI computers. I find it all rather prophetic, don't you? Let's see. So first thing, if you haven't already done so, you will want to grab MSYS here. All right, and run the installer. There's some instructions on how to do that, and also how to get set up for doing C and C++ programming, if you want to do that. Okay, then having done that, then the next step is to first. Let me go. If you look here, it'll probably be in your recently installed items, but if not, you can go down here and type MSYS2, and there's your full list of applications, and we want this blue one here that says MinGW64, right? I'm just going to launch that there. And then it's running down here, so I'm going to right-click and pin it to the taskbar because we're going to be using that a bit. Get this over here a little bit. Okay, good. So then, having done so, you're going to run a few things. First, you want to update the program itself, and then it'll ask you if you want to close the window. Yeah, and close the window, and then you open it again, and then run this, and that'll be all updated. And then we're going to grab a few tools here specifically suited for doing assembly programming. So for those of you that already have NASM and QEMU, you're familiar with the same tools. It can be used from the command line here, but we're going to grab a different flavor that is compatible with our MinGW here. See? So when you run Pacman, this is convenient because it will install all these nice programs and modules all ready to work seamlessly with this environment. So it's kind of like a one-stop process. So we're going to have our assembler and a emulator. Sorry. There it is right here. Emulator, and then a few tools. So right there, the debugger. We're going to call one or two commands. We don't necessarily need to use Vim. We can use Notepad or whatever is convenient for you, and then we'll tool for reading binary. And all we have to do is run this one line, and it will install everything for you automatically. Now, for those of you who understandably are not into typing mile-long commands, I have chosen to be merciful. I have provided on my GitHub a repo with appendix of all of the command line cut and paste stuff that you can use for this tutorial, this video tutorial. You just go here, okay, and if you click there, you go download zip, okay, and then what you will end up with is this folder. It's very small, actually. It's just some HTML files. I suppose I could have used a markup and just done readmes, but I'm much more fluent with HTML, veteran HTML programmer, so it's easy for me to make these tutorials for myself, really, my own references. So I took a bunch of, there's the tutorial, the complete tutorial, and then also in there, hang on a second, is the opcode manual, layout, a nice table, and appendix of some more modern architecture stuff that's your basic and more complex stuff. And then in the tutorial itself is where'd it go? A link. Thank you. Yeah, and I made this to be full screen, you know, assuming most people have a pretty big monitor. If not, it's all mush. Sorry about that. Laid it out in Chrome, you know, so it's there, everything all in one place. Nice big screen. References, and if I want to know what any one particular one, it'll jump straight there. And this is helpful to me. I took a whole bunch of various references and tossed them all together in different ways. Here, this shows me the decimal value as well as the hex value for chaos coding, right? And I also took the time to provide actual examples, which none of these technical manuals do, you know. So you could do all these and see the resultant machine code. I might add machine code to this list as well later, you know. And in the index, you can go, there's an appendix of all the more state-of-the-art stuff that isn't 16-bit, you know, all these additional things in your processor, as well as, what was I? Yeah, there's all your examples there, you know, so helpful cross-reference. Here it's linear, you know, 1 through 256, and here, nice table, you know, and yeah, hopefully that will be of some use. And then you can just go and copy and paste all of the instructions. Yeah, here, I want to run this from the command line, just copy it out of there and paste it in there, save you some time. There you go. So, having installed and updated about a handful of the 35,000 packages available for MinGW, we should be ready to go. We can just verify NASM, our assembler compiler, is assembling, and also make sure we have an emulator. Yeah, everything seems to be up and running. So first thing, if we haven't already done so, you might want to make your folder to put your stuff in, of course, your name, not my name, right? And then we're going to navigate to that folder like see, so now we're in the assembly folder. Now this is a Unix syntax, so it's a little, takes a little getting used to. Here, let me put this over here. Yeah. Whereas you're accustomed to this, now it's the other way with the slashes, forward slashes instead of backslashes. So it doesn't have to be a problem. So here, let me, if you know your basic command line syntax. If not, I'm not going to defray too much, but you know, if you go cd space dot dot, there it goes up one directory, so I can list whatever's in there, and there's some folders. There's the new assembly folder I just made and some stuff, whatever. So I could cd a tab, and autocomplete takes care of that. Back in the assembly folder, the usual, you can find out more about how to navigate around in the internet. But basically, let's say you have a folder of your own that you want to use, not the one the way I'm doing it here. You can go to your folder wherever, like that, right? Here, let me open my folder there. And then up here is your path. So like if you click there, it turns to a regular Windows path, right? You can copy that, and then instead of having to go here and convert all these backwards, you can instead just go here, and I could go, whoops, here, just to, let me go, if I go cd back to the starting directory, there, see, I'm back at the root. If I want to get to my folder, just copy the path and go cd single quote and shift insert, right? Single quote. Yeah, see, and now I'm in assembly. That allows you to use your normal Windows syntax that way. Okay. So I got my Explorer window open. Good, just for visual reference. So I can create a new document, and I'm just gonna call it machine code. Yeah, like that. Enter. And so here's my machine code document, whatever. First thing we want to do is declare a data byte, like so, space. So there's my data byte. Next I want to define the file size, I guess. And the way I would do that is to just fill this up to the appropriate file size. So I got one here. If I go Control A, that selects all, and then Control C, and then Control VV. There, now I got two. So Control A, Control C, Control VV. Now I got four. So 8, 16, 32, 64, 128, 256, 512 zeros. Okay, so I'm just going to go Control S to save, and then Alt F4. Now, let's see. So from here, I could list everything in my current assembly folder, and there's my document. Wonderful. So next I'd like to assemble that into a binary file, and that would be xxd, let's say minus r minus p, and then if I go m tab, autocomplete finds it, and then I'm going to create a binary file, and I'll just call it binary.binary, to make it easy. Okay, so there's our binary there. Say, it's full of zeros. We can have a look at it. And, oh, what happened to all our zeros? Well, this is a text reader, and there's no text there's no text data in our file. It's just a lot of nothing, so it can't read it, so Alt F4 out of there. Instead, from here, I could just go hex dump our B tab, wow, like that there. Now it can see it. So it basically says, oh, it's a bunch of zeros, and this dust bunny here means etc., 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 right? Until it gets to, this is in hex, so it's line 512 in hex, okay? So now also, here, let me go up arrow one time, here, and then it remembers the last command, so I could go over here, and instead I'll say minus capital C, and now it's in bytes. Yeah, like we were working with over there in bytes. Observe real quick, see it's like 8 bytes, 16 bytes across. Okay, that's a handy reference, just let's file that away in the back of your mind for later. Okay, 16 bytes per line. Got it. Okay. So let me run our emulator, which would be QEMU, QEMU minus system minus. I'm going to use I386 here, and then you call the Food and Drug Administration. Will be basically we're telling the emulator to stick it in its floppy drive A, I guess. Then we'll B tab and run it. Okay, so it actually looks on the floppy and finds something, but it says reports back it's not bootable. Okay. And then it looks on the virtual hard drive, and looks on the virtual network. It looks virtually everywhere, basically. One thing I should probably point out real quick, should I happen to click here in the QEMU window, everything locks up and you can't get out, observe up here, it says press Control-Alt-G to release grab. There, now I'm out again. I can Alt F4 out of there, and now I'm back to my command line again. Okay, so let's see here. If I just now, I can up arrow till I find Notepad. There's my document again. If I Control End, there, I'm at the end of the document, and I can just back up a couple and replace that with 55 AA. There's our magic number. So now I could, I'll just Control S and Alt F4 out of there. And what I want to do now is call the assembler again, of course. Yeah. There, XXD. There, it's all assembled, and let's see if we can run it now. Oh, look at that. See, now it boots right away. Nothing on the virtual hard disk, but on the virtual floppy, there it is. It booted right up. Nothing to see, but, not looking all over, virtually everywhere for it. Okay. Alt F4 out. Good to go. Now, one thing to note, you get all this error message stuff. We could make that go away. We don't have to. It's a little bit longer path, like that. There. Let me just call the same thing again. There, and it boots, and you get no error message, So, like, you get the things telling you, hey, it's dangerous, you don't want to do that. Your password privileges have been revoked, and it gives you a stern lecture about how to, write commands in the future, So that can kind of lower your self-esteem, I guess, but it's inconsequential, So another thing, like now, let's say I went to, I could go Notepad, now my B tab, my binary, and look at that, there's just some actual printable character in there. My U, the 55 we entered is, that would be 85, is the hexadecimal 55 with 85 and decimal is also a printable character there, and the other one is the feminine ordinal indicator. Ooh, which that's what a feminine ordinal indicator looks like. Should anybody ever know? But not everybody knows, I guess, because if I go over here and cat the beta, oh hang on, yeah, cat try and look directly at it, you know, and has an identity crisis on its femininity, I guess. So while we're here, let's go ahead and put some. We got our bootable code. I can go ahead and add a little bit of more code to that. I'm just going to pump some code right in. You know, like hang on one second. Let me Control U to clear the line. You know, if I go print F hello, and it prints hello. Yeah, okay. So that's a basic print function. Yeah, printf. Okay, print function, and it'll automatically just print something to the line if you don't specify anything. But it also has some other parameters that you can pass to it. So I'm going to pass some code in there. Let me just there it is. Pass a little bit of hex code into our machine code, and here this says this part that says do not truncate basically says if I didn't include that, it would just overwrite the entire file with only the part that I'm putting in there. But you know, this says keep the original file length, and I guess that says basically everything. I'm doing this bunch of BS, I guess. I don't know. Let's see. There we go. Excuse me. So we have now, if I go cat, hang on, I'm getting ahead of myself. Let me just go back in time here using the arrow key up till I find XXD again. There. And then we'll keymu that. Keymu that. Yeah. We have a happy computer. Okay, so while we're here, I guess, let me just Alt F4 out of there. And as I demonstrate, I have these commands now in memory. There's XXD, and if I down arrow, there's the previous, right? So now that's nice for now, but if I close this window, all of that will go away. So it'd be kind of cool to preserve some of this long commands for later, you know, so I have to do more typing and stuff later. So I'm going to just highlight this one, and if I go Control Insert, that's in memory. Now it's copied it into memory. That's the Unix equivalent. And then now I'm going to Control U to clear that line. And now, let's see. I'm going to use that printf command again. Print F. And we'll say shift. And then if I go shift insert, there's the thing. Okay, now this is one thing. It made a new line. It doesn't always do that, but just here, let me go. You can go either left arrow or backspace, back to there. Let's see, and I want to add a couple of new lines of my own, but I'm going to do it manually. I'm going to go back, slash, n, backslash n. That'll add 2 carriage returns after the line, and then we'll close that up there. So if I just ran that, it would, whoops, I'm sorry, close the quotation like that. Yeah, that would just print that to the screen at the moment, but instead you could take that and create a new file, and if the file doesn't exist already, it will overwrite a new file called snippets. Like that, yeah. And then that pops up over there. And there's our line of code. And it also has the 2 returns after. See, so now if I add something else, it'll be here instead of on the tail end of that. I don't have to deal with it later. Okay. So why don't I do that? Let me go grab that other command. Where was that? Kemu is real handy. I'm gonna grab that and control insert into memory, and then control U, and let's do that again. Printf, and you're shift, and then shift insert. Okay. It made a new line. Okay, when it does that, in this case, it's kind of cool because I was going to add a new line anyways. So I'll just go ahead and add the other new line. You see what I'm saying? It's the equivalent of going back and adding two new lines. If I just leave that return in there, that is interpreted as a new line. So that's something interesting. So I'll close that up, and this time, remember this command is create a new file or overwrite the existing. If I don't want to overwrite the existing, I can add one more, and that will append that text to the existing file, which of course is my S tab. So now, if I go look at snippets here, you see there is, I can add more commands to it ad hoc from the command line, you know. But the beauty of this is, of course, if I go cat my S tab there, now if I want to run any of the commands in my list, I can highlight it or triple click 1, 2, 3 on the line of call and just go shift insert there, and it brings it down to the command line and hit enter there, and it executes. Pretty handy. So there we go. Let's do the other one real quick while we're here. So I'll select that and we'll go shift insert enter. There. Happy camper. Yeah, okay. One more thing I probably might want to mention. Let's say, for instance, if I wanted to add something that had quotations in it, that could throw it off. Like, you know, like if I said, she said hello, like that, then that quotation would throw the thing, you know. So, I'm sorry, here, hang on. Let me do this right. If I said, printf, she said hello again, like that. See, that would throw it. No, because there's the closing quotation. See, so when that happens, you could go like use a single quote, and then we'll say, and then you can use your regular quote like that. And then close it with a single quote. Yeah, and then we'll just append that to our S tab. Yeah, let's have a look. Yeah, you see. So it appends it with a quotation and doesn't throw a fit or give you the wrong thing. So I can just get out. Oh, let me see something. So you go, you click here, and then you go Control N. Shift. Oh, Control N took me to the end of the line, and Shift and there, select the whole line. I'm just like playing around sometimes. Get rid out of there, delete, Control S, Alt F4. Yeah. All right. So let's see. Here I've written a very rudimentary bootloader, written in pure hexadecimal machine code. Why do it that way? I just find it interesting because it took like years to find answers to do some of these things that I knew ultimately was quite simple. And sure enough, I was right. Here, today I could write an entire bootloader using a single line command. There, I just wrote an entire bootloader, working, fully functional bootloader in assembly code. Crazy. Okay, so let's see. I have binary file, let's say, and of course I can look at what's in there in hex dump, or whatever format I choose. That's minus capital C, my B tab. Yeah, I can look at it in hex. Maybe I'd like to get this into assembly. Okay. Now, there are programs that are better suited for decompiling, but we do have some rudimentary disassembly tools available. That is NASM, Disassemble ASM. Yeah, and B-tab. Okay, so it scrolls all the way down to the bottom. Oh, while we're here, why don't we observe... there's a bunch of zeros there, and there's our 55AA. This is in machine code here, and then there's a crude attempt at doing some assembly over here, and there's our line numbers. Can I page up? No, I won't page up here, but there's another way to do that. Let's go, instead, I'll go disassemble with the same command, but I'm going to pipe it into a little program called less. Okay, and that just, whoops, oh, my bad. No, I don't know what I did. Let me go Q out of there. Let me do this again. Disassemble to less. I think I pasted the wrong thing there. Okay, so now I can see just the top part here. Yeah, and then it also, you can scroll down with the wheel and scroll back up, or you can use the arrow keys. Yeah, arrow up. I could go space bar, and you got a page at a time, or B to go back up to the top. I could also hit the end key and go all the way to the end, like that. And home, yeah, back to the top. Hey! I just discovered a new key. Never tried that before. All right, so the thing about this is, here you get this crude attempt at doing some assembly over here. This is pretty good. This is not. But we do know that's a bunch of zeros and padding, right? And just from experience. And at the bottom, our magic number. Okay, so sometimes it helps to compare, if you know what's going on over here. If this isn't clear, you can just, see what's being written to the actual registers, Okay, now this is kind of useful. We could export this out to a text file, but it's got all this hex machine code here, and as well as a bunch of line numbers also written in hex, but we can strip that out of there and only see our assembly code. First I have to Q out of here. Okay, so I could go all the way down to the end, but I'm still stuck in this page reading app. To get out of there, you hit Q. Yeah, and you're back to your command line. Okay, so I will now disassemble, and it strips out all the line numbers and the hex code there. So this time I'm just gonna up arrow, do the same thing, but this time let's pipe that into our T-tab over there. Okay, so now if we have a look at it here, now we got some crude assembly code. Yeah, there's our Mr. Happy, and now say I want to get rid of all this. We click there and go home, and was it Shift End? Yeah. Now I could, if I went to replace or Control H for future reference, and that would replace all these, but leave the spaces, So if I don't want to do that, I could go down here and drag up. That captures the return as well. And then let me go Control H, and now just replace all with nothing. There, zips right up there. Nice. And we know what this is actually. It's the booty. Yeah, I'll just grab it right out of there. That's all we really needed all along, huh? Okay. And there we go. So there is, in theory, it should be a functioning program. Now, of course, I took some liberty here to kind of compress the code a bit, here. So I would use the least amount of machine code, for demo purposes. But, you can effectively see what I'm doing here is, just copy that. Putting this bit into the higher part of AX, and then into the lower part of AX. It's OX, OE, yeah, and O2. There, yeah. So there. Just compressed it a little bit, So to break it all down, there's our Mr. Happy. Let me just save that and go ahead and NASM. I can Alt F4 out of there, and we will just turn that into a binary and run that in Kemia. And there you go. We have successfully decompiled our program manually. Like I say, if you're into decompiling, there's programs that kind of, help you lay it out and stuff, but there you go. Quick binary to assembly code, using disassembly. Okay, but back to topic. What exactly is machine code, and why are programmers so fascinated with using hexadecimal? All right. You don't have to. Here, I could work in decimal. There's my binary program expressed in decimal. Here, let me just look at the first 8 bytes of my program in hex, right? Okay. Here, actually, let me just, I'm going to Control L, and that, different from clearing the screen because all your stuff is still up there. It just kind of adds to the length of your desktop, basically. And here, now that I've done that, run a little script here. There, that is essentially what your computer sees, stream of ones and zeros. This is a pretty much exact representation of what an internet data stream would look like if I were to try and send 8 bytes of information over the internet. So, you could think of it like your computer, when you contemplate computers thinking in ones and zeros, they don't read the zeros at all. So here, if this is some internet data stream, let's just say we're sending at a baud rate of 60. That would be 1 bit per second, right? So it would be like beep, beep, etc., and then beep, and then beep. You see, so the zeros are implied by the amount of time that passes between one blip of information and the next, whether it be an electrical impulse on a copper wire or a blip of light on a single fiber of glass, But the spaces are only for our convenience, really. Here I could separate it. The spaces are just there, so it makes it a little easier for us to read. But here I'm looking at bytes, right? But you got your 64-bit processor would process that entire chunk. It would crunch that entire chunk all at one time. That's the beauty of 64-bit, So anyways, let's see. If I wanted to see that same first 8 bits in capitals, like that, yeah, a little easier to read. There, let me dump, I'm going to dump the entire thing. Yeah, okay. So there, now I can see, but why use hex? What's up with using hexadecimal for things? Here, let me go over to this table. Now, there's a maximum amount of information one could express in a nibble of, a byte of information. And that would be from 2 bits, excuse me. That would be from 0 to 15. I'm sorry, 0 to 15, So a total of 16 possible, right? So that's not much that you can express as far as higher numbers. So what they do in the hardware level is you create a hardware table, essentially, and you're saying anything in this row, is the first nibble, and whatever's in the column is what's in the second nibble, right? And that gives you your byte, your total information in a limited amount, but that gives you quite a number of commands that you can call, which is and that's working in 16, right? 16 across, see? So that's everything in group of 16s, and hexadecimal is a 16-base language. So that's kind of a reason. Here, let me that's our opcode tables. I'm going to just copy our T-tab, Mr. Happy there, and let's just make it a little happier, I guess. Yeah, so, notepad, my H-tab. Yeah, okay, so here, as you recall, I deconstructed this in the earlier part of the video. Let me make 2 Mr. Happies to start. All right. So, as you may recall, previous segment of video here, we took, it was OXOE there, right? And then the other one would be OXO2, like that, right? But then originally it would have been both of those together in one part here, O2. Okay, now I'm just going to separate this with some couple of zeros, db00. Good enough. Let me just save that and Alt F4 out of that for a second, and we'll go NASM that. NASM minus F binary, our happier file, minus O to our B tab, yeah. And then let's, I'm going to hex dump it, but instead of filling the whole screen up, I'm going to do this compressed view. Yeah, okay, so the dust bunnies indicate, etc., etc. But as you can plainly see, the first option uses an extra byte of machine code, right, than the second. Here, basically, I'm really saying the same thing, but here in the first line, we are copying value into the lower the higher register, and then we are copying a value into the lower register, right? Here we're just saying, so this command accepts 1 byte. This command accepts 1 byte. In this command expects the following 2 bytes to be, to go in there, and it says load AX, right? This and that, right? Observe it's in the opposite direction now, right? Instead of E2, no, it's 2E, because we're moving a word value, and it's the backwards architecture, right? But anyways, to make a long story short, the first, oops, not that, so the first version actually takes an extra tick to the processor, so this version runs faster. Yeah, doing the same thing. So I'm packing the code there, various things. Maybe you want to develop this way, I prefer to use decimals for smaller values, but what would this full value be? I'm going to go over here to my calculator. Yeah, you got standard mode. It looks like that, but if you click here, you got programmer mode. I go to hex and then paste, and it tells me that EO2 is 3,586. You see, so if I put 3,586 there, it's not readable. You see, it's an arbitrary number. It makes no sense to look at. But doing it this way, it preserves the higher and the lower. You see, so that's the advantage of working in hexadecimal. I hope I've made my point there. Yeah, here, so I could go, yeah, so in either case, okay, in the first, I do it this way, what's going to end up in AX will be this, right? And when I do it this way, what's going to end up in AX will be this. You see, the result is identical, right? We've just taken an extra tick of the processor to do the same thing. Yeah, okay. So, let's see, yeah. So that's, there I'm packing a couple of values, and then other things, so you develop this way you make it nice and readable, and then once you got it all finalized, then you go, okay, I'm going to pack it up, and that will optimize your program, and also like unrolling functions and such, as I discuss in my optimizing programs for speed video in this series. Okay, so we don't really need any of that. In fact, I could say bye-bye love, bye-bye happiness, gone. All right, let's see. Okay, so we have made our bootloader, really, and our kernel is going to reside here, OXCEO. We'll automatically load at OX7C. Yeah. Here. Let me. So our origin of our bootloader, right, if we were to explicitly define it, our origin OX7COO. Yeah, see. But I'm working in whatever unprotected mode, whatever you want to call it. But what exactly is OX7C? Let me just copy that, and then if I go over here and go, first let me just go print F, call my print function and print the value. Okay, and it prints the value. Okay, that's what a print function does. Now, let me do it this way. I'm going to just take that and put it there, and instead we'll say $, and then we'll take that and put that there. Yeah, so that tells us the actual value of our, anything in here could be some math, you know, like for instance, if I were to go, what's 3 times 5, see, it does the math, right? Okay, so it also recognizes hex values, so that's nifty. It's not built in, it's one of the functions from the additional things that we installed at the beginning, so very handy for doing calculations within your code, your command line, you know. Anyways, so there's our value. This is where we're actually booting in memory at memory slot number 31,744. You see, so actually here, let me. I got my. Let me open this and. There you go. So we're loading here in memory. You see, when your computer boots up, you know, you have this is how much built-in memory you have. You know, if you find an old computer in the junk and somebody's removed all the RAM, that's what you get, this bit here. The rest is not free, and you have to pay for it, you know, see. When your computer boots up, it takes some code that's stored in hardware, you know, and it needs to be running in memory, so it gets the first little bit, right? And then everything after OX500 is yours. But it's going to look here first to see if there is a bootloader, right, at OX7C. Once having done that, you're kind of locked in to here. You know, you can't get out of this 512 sector. So what we need to do is jump out into a free sector. Now I could jump to OX500. I could jump here, you know, and then work my way down, you know, but traditionally, well, one way to work is instead to jump to the sector immediately following the boot sector, and then use this area for memory. This is upside down. Let me just, I prefer to work this away there from top down. There are zeros on down the list. So all this stuff loads system stuff, right, that tells you how to communicate with your USB and devices and how to print stuff to the screen, all that, you know. And then your bootloader is coming in here. We're writing to here, right? And then we're going to jump out to here. Okay. So once having done that, this bit is obsolete, you know. So all of this here, all of this area can be overwritten and used for scratch or temporary memory storage, right? And then we can reserve some other space for other things, variables, temporary space, and put your stack here, right? So you'll say your stack starts at 9EC, and then every time you add something to the stack, it adds it downwards from there. Okay. So that's kind of one way. May or may not work, but we don't need to worry about that for the moment. What we're doing is trying to get from here to here. Okay, so let's write a little program that resides at 07EOO. Okay, so what I want to do first, let's see, so where was I? Oh yeah, here, yeah, so if I got, if I go printf this bit and say, this is where we're booting, right? There, you know, and we're going plus 512, yeah. That's where we're going to end up. That's where our kernel will reside at memory slot 32,256, which if we, let me go, do it this way. I go print F quotation percent X percent and do the same thing. I'm going to take this value, which equates to this. All right, I'll just go put that there. 7E. See? So we're coming in at 31,744 in memory, and then we're jumping to 32,256 in memory, which is 7E. If I wanted to be fancy, let me up. I could go back here and just add the OX in the printout, just to keep it readable there. So why don't we make our kernel while we're here then. I'm just going to make a new document, and I'm going to type until I reach the end of file. I'll just say EOF. It could be anything. It could be Bob, whatever you signify. But, keep it kind of standardized. And make a new program. Program 1. Yeah. And then when I hit enter, it creates a new line, and now everything I start typing will go into my program. So we'll start simple. 9. Before we used 14 for our teletype. I'll use a little bit different function here. This will allow me to print color characters, and then move A into the lower register. Before Mr. Happy was 2, I'm going to use a different character so we can verify our printout. Oh yeah, also, let's say if I go, whatever, make some kind of mistake, I can control U to undo that line or whatever, and, start over. So, let's see, BX. Now I can put a color value in there, and then one more thing. Sometimes you don't always have to put a value in here, but sometimes if there's already a value in there, it could get wonky results. So we want to say quantity. Okay. And then I'm going to say int 16. That's CD10 in machine code. Let's see. And now we don't need a bootloader on our new program because we've already bootloaded off of our bootloader, right? We've already provided the magic number there, so that is behind us. So now I'm just going to signify end of program. So I'll clear the interrupts and say halt. Here we go. And then so now when I type EOF, that signifies end of file, and there's our program over there. Wonderful. Okay, so now we got our test, our bootloader, and we got the program we want to jump to. Okay, so let's see. Let me go here, Notepad, RT tab, like that. Now, we have explicitly defined our origin here, OX7C, right? And then we're jumping down here to, as we determined, OX7E. That's where our kernel will be. Okay. I want to do some stuff over here, but now my command prompt is gone. Why is that? Well, because I called Notepad as a process over here. See, so I can close that and don't save. And so otherwise, you could just open it from here if you want to do editing. But let's see. So I have my kernel. Now I want to jump to my new program, right? So that will be, to make a long story short, let me just, let me go start notepad like that. Yeah, and now it's not attached to the process any longer. I can continue doing stuff down here should I want to, you see. So in my bootloader, paste some code in here real quick. There, this will allow me to tell our kernel where to load in memory. And as we said, we want it to load here. We could put it there at the very beginning, you know, but we're going to put it immediately after our program there. Yeah. Our kernel dot binary will reside immediately after our binary. Yeah. Okay. So here I've compressed some of the commands here, as you can see. Before it would be move ch0, move cl2, and, you know, well, since the first part is 0, I just simplify that by, you know, see if packed some things. Now here I left that like that for readability, you know, but to make a long story short, I could just just do that, you know. It's still readable that way, you know. But so that is read sector from disk. Read sector from disk and number of sector to read. See, like that. There, now it's combined. See, so that means a faster bootloader, you know. And also, like here, you're probably, if you've ever seen any of these tutorials, you're probably used to seeing something where you're redefining your value down here, or even doing this, you know, which is the same thing, really, you know. But that is what's known as immediate mode, right? Where I'm putting this is immediate mode. I'm moving a value into the register, but it's always faster to go between registers. And since I've taken the time to put that value in there, I'll just grab it out of BX. There, saves another tick, you know. See, optimizing, you know, and there I could compress that too, yeah. But just for showing you how to get it done. You know, so let's get to the point here. So then, now that we have our bootloader pointing to our kernel, okay, I'm going to Control S and Alt F4 out of there. So now we just want to NASM. NASM our type of file is a binary, and we want our T tab. The type and the output will be our B tab. Yeah. Whoops. Okay, I got you. Line 6. Let's see what I did here on line 6. Line 6, I did that. Yeah. Let's save that. Go back. Get out of my way. And up arrow. Yeah, okay. So that's all NASM'd, you know. And so then we can do the same thing to our kernel, like that, right? And then now we have our binary here, and we have our kernel here. I'm going to combine the two of these, so this will now come immediately after our 512 boot sector. I'm going to do it kind of the easy way here. I'm just going to concatenate cat our B tab and our K tab. Yeah, yeah, into a new file, and I'm going to call this combined dot binary. Yeah, so there's our new combined binary. I could hex dump it, I suppose. Hex dump our C tab. Yeah, so there's our normal program there. And we have concatenated our other program there. Yeah, awesome. Let's see what happens. Okay, so now that we have our program concatenated into one, now there's one thing here. Let me go. This is the normal way we would run our binaries using drive. Yeah. Okay, it boots, but we got our happy computer there, but unfortunately we're not seeing the printout indicating that we have booted into our kernel. Okay, but no mistakes, just happy computers. The way you fix that basically is instead going to use the Food and Drug Administration approved method like that. But before I do that, I could then do all of that, all of these three steps here, 1, 2, 3, in a single command, you know, to save time. You know, you go NASM your file into a binary, and NASM your program into a kernel, and concatenate everything like that, right? And then I can run Chemia, yeah, like that. And there we go. My heart boots for you. Okay, so we have verified that the bootloader is running with some positive output, and then let me Control Alt F out of full screen mode there. Yeah, we verified that the bootloader, Mr. Happy is there, and we have successfully bootstrapped into our kernel, right? Indicated by our booting heart there. So now we are out of our limited 512 bytes bootloader space, and we're now out into a much larger world of 638K of memory. All right, we're still in 16-bit real mode though, and our bootloader, having served its purpose, no longer needs to reside in memory and can now be overwritten and reused as additional free memory. Yeah, so see you later, emulator. Awesome. Yeah. Now, of course, I use the FDA method, so you get the error warning, but it's inconsequential. It doesn't hurt anything. It's just a little message to sell. Now, one thing that's quite confusing, and actually took a little while for me to wrap my head around, is the fact that here we're defining where to jump on the hard drive. Right. Now let's see here. Yeah. So this is a very, very extremely crude representation of your hard drive, you know, and you have tracks and sectors. Basically, we could say that our boot sector would be there, just okay. And what we're doing is we're jumping out of that boot sector over to here. See, that essentially, once we're in here, that renders this obsolete and it becomes free memory. Okay, so what's confusing about all that, just get out there and go to Explorer over here, is, like I said, there's, you have these tracks and sectors, and to simplify, here, it's like this. There's your sectors, right? And then this is a block. So technically what they call a boot sector is not a sector at all. It's a boot block. It's only called a sector because due to legacy from older hard drives that had very limited amount of memory, right? So your modern hard drive will have lots and lots of blocks, so, and this is actually a gross underrepresentation of how much there actually is too. But as you can see, it's like for efficiency, it's not laid out in straight lines, because obviously you can fit more out here on the outer tracks than on the inner tracks. So they finally figured out that it's more efficient to divvy it up a little differently. You see, you'd have basically there would be spaces between memory here, and it would be packed quite tightly there. So they'd make it so this is the memory you don't use very often, and this is the frequently used memory, because it's less likely to be corrupted by neighboring data or what have you. But anyways, this is all moot points, really. So here's the funny part. Like if I go on the internet, here, let me refer to my image again real quick. See, there, see, block. That's our boot block, all right? But like I said, if I go on the internet and I'm trying to research this, it says, okay, disk sector, that's a track, that's a cluster, that's good. Here, this says that's a sector. That's wrong. That is a block, right? Oh, here's another one. It says these yellow things are sectors. No, these are blocks. You see, sector? No. No, you could call this a track sector. Some people do who want to like to cross tracks, so to speak. But here's where I finally figured out the actual terminology. I had to look it up in German. The technical people who can give you the straight answers here. All of these are completely messed up. Here, this person kind of correctly calls it a track sector, right? The difference between but he calls this a disk sector and this a track sector, so that's where the confusion can come in, so trying to find any terminology, sector. Okay, these are platters, what you would think of as disks, okay? And then then the confusing part is like, here, let me go. Here, this was extremely helpful. Here's your Ning Kong Chang, and over here, this part, your Huing Ha, but basically, what this does illustrate that the other ones don't is this is a cylinder. The purple bits, when you have contiguous tracks on multiple platters, that's what's known as a cylinder. Okay, and then, so, yeah, like I say, they all have their own, hang on, why is this Google Lens here? I don't want no Google Lens, I just want a fresh, thank you. So as I was saying, they all have their own methodology of storing data, and they're all different, why? Well, probably the American patent process, everybody sorts their data a little differently. Here's a Seagate, and that one's a Toshiba, and each is probably patented, it's like, not necessarily because one's more efficient or whatever, just because you can't use the other guy's patent. I would hate to see what the shock absorbers on an American bicycle look like 50 years from now. I'm telling you. But anyways, it doesn't matter, all this round stuff. Essentially, it's just sectors of data that are linear to you and to the computer. The method of storage is irrelevant. And what's even more irrelevant, and this is the source of confusion, again, here, we're telling the computer where to jump on a disk. We're not jumping to a disk at all. We're jumping to memory, right? So, see, this is from way, way back in the old days when there was no such thing as RAM. You know, you would read from a hard drive and write to a hard drive. You know, today we have read-only memory, which is way faster, you know, but in the old days, you had a hard disk that was limited by 512 bytes of memory, and if you wanted more memory, you would have to jump over to a different hard disk, not on the same spindle, you know, but on a completely different unit, you know, and not like today that the hard disk the size of the fingernail on your little finger. No, it'd be like the size of a pizza, you know, and there's your hard disk. And then when you wanted to jump over to another 512 megabytes, you would jump over to another suitcase size unit there. I hope that clarifies all that, why all of this is confusing. In fact, modern, your digital solid state hard drives don't have cylinders at all. They don't have half of this stuff, you know. It's far more simplified. But your computer still needs these numbers, you know, to know where to jump to. So that's the confusing bit, is that we're not jumping to a hard drive like this says. We're jumping to a location in memory, in read-only memory. Okay? Okay, so alternatively, you know, we're working in hex, but no one's forcing you to work in hex. You could work in decimal if you wanted to. At the beginning of this, at the demo, at the beginning of the video, I showed a method where I created a file using full of a bunch of zeros, and you know, some of these long commands, maybe they're a little intimidating at first, but when you break them down into their parts, then it could be a little more understandable. I can say echo hello, and it says hello, right? And I say yes, hello, and it goes nuts on me. Now it's infinitely saying hello. Maybe they should have called this one echo. What do you think? I don't know. So anytime you get into some kind of infinite process, you can go Control C to get out of there, and you know, it's like that, right? So here, and I could do that same yes command, and then use the pipe. Let's see, that's right above enter, and you hold the shift key, all right? You get that into another function called header, whatever, and that limits infinity to the designated number there. So now we've printed something out 16 times. Okay, so let's say I want to print a couple of zeros 16 times, but instead of being on different lines, we can strip out. Here I'm going to take that and then pipe it into something else that says strip away all the carriage returns, right? And then you end up with that, right? Okay, so if I want some spaces in there, I'm just going to basically do the exact same thing, I guess. Let me arrow up. Only here, put this in quotes like that and just add a space and do it that way. Yeah, so there, see, so I can generate a whole bunch of zeros, right? So if I wanted to generate my 512 zeros, it would be this bit here, right? And that would print it to the screen, and but then I could also create a new file and pump it in there. Yeah, I've already. There. So that pumps all my zeros. Now I got a file full of zeros over there, see? Now, let's say I want to work in decimal. I could do the same thing. Let me go up arrow, and instead of 1 0, I'll just populate a text file with single zeros. Let me close that and reopen it. Yeah, see, so now I can work in decimal mode, right? Instead of 55AA, that would be 17085. I'm just going to put some a few bogus values in here, and then we'll do some other stuff here too. So don't quote me on these numbers. So I'm working in decimal now. I remember before it was 2 for Mr. Happy. Let's make it 3, and whatever, 14 there, and 205. And I'll just save that and Alt F4 out of there. Okay, so I have, it's working in decimal. I'm doing machine code, but you don't have to work in hex, you know. Okay, so I have my text file that's been edited, and I can turn that now into a binary like this. Yeah. So now if I hex dump minus capital C my B tab, there it is. See, I can see my code there. Okay, now say I got some errors, you know. Now I could go through the trouble. Let me just go through the trouble on purpose here of converting this back to text again. Well, I mean, I got my text, but let's say if I wanted to, I got a binary I want to convert to text. Okay. Well, there, and then that takes my binary, converts it back to text, you know, and then you can edit it down and then re-import it. But you don't have to actually do it that way. No. Instead, here, let me go. I'm going to go cat my M tab. Yeah, I see. I can view it from there. So let's go. I want to overwrite. Hang on. I don't want to cat that. Here's what I want to do. I want to hex dump my B tab like that. Okay, yeah. Now, I'd like to overwrite some values here, right? I could just pipe them in from the command line here, like that. Whoops, not that command. Control U, another command over here, like that. Okay. Using printf, I'm piping in some values into my binary. Do not truncate. Now here, these are my hex values, but to say designate that it's not text, I'm using this, which says that these is data, raw data that I'm piping in to our file. Okay, so here, what did I do? 03. Here, let me just change the 03. Oops, hang on. To a 02, like that. There. I just overwrote some bits into my program. Now let's hex dump. There, see, there's my 02, see. 02B8, yeah, see, yeah. So now, let's say, now that I have the ability to edit directly into my files, you know, I didn't need to go through the trouble of creating a text file at all, really. Here, I can read from the line here, and I can pump values in. If I wanted to, I could have just started like this. There, this will write a file of all zeros, you know. So here, let me go hex dump my A tab. Yeah, it's all 512 zeros like that. But I don't need to do it that way, you know, because we've already done all that. I'm just bye-bye zeros. Here, let me go. So I could look at my entire hex dump. My entire file is a hex dump. There's the whole thing at one time. Oh, okay. Now I see, a couple of errors, right? Like this should say CD10 for one thing, right? Okay, so before let's say when we were working with a text file, I could pump some text in like this, right? And using the math function, let's say it's 3 places for each value if I was working in text, So if I wanted to be here, right, that would be 4 times 3. 0, 1, 2, 3, 4, right? So if I were writing into a text program, or a text file, right, then you could calculate the position times 3 this way, right? But I'm not going to do it that way. You can just, but when you're working in binary, it's a 1-to-1 relationship. Yeah. If I wanna print into here, I could say position 4, right? Let's do that, and then we'll go look at it again. There, see, I've overwritten the 0 with the value of 10. Now down here, I got my AA55 bass backwards, because perhaps one might be working in words here and get things reversed sometimes. Okay, I just want to flip that, So now let's say I don't know what number that is, Here, first, instead of this big view here, let me go, there's a more compressed view, yeah. AA55, okay. I want to try and flip this bit, all right? Yeah, so as I was saying, you have your, you want to replace a particular value and you're not sure where to find it in your assembly, you can hex dump your entire thing, and so I want to replace that value 510 there, so you can use that command to individual line numbers for each byte, and so where specifically to put your value. Let's see. Oh yeah, so I could just overwrite the tail end of that now. Hang on, like this. Right, right. But I don't need to say do not truncate necessarily because it's at the end of the file. Yeah, let's have a look. Yeah, 55AA. So program's all fixed, right? Also, let's say you've already shipped your program or whatever, and you found an error somewhere. Okay, 2 should have been a 3. Okay, hang on a second. So you can create a patch here. First, let me make a file here. Brand new file. Yeah, there's my patch. See, and here, let me let's have a look. Hex dump -C my tab there. Yeah, it's just short and sweet little patch, right? I want to patch it in there, So I could now overwrite. Sticky mouse here. Hang on. I can now overwrite my program with another program like this. Wow. Yeah, I could take my patch and overwrite my binary and do not truncate like so. Now, if I hex dump my file, there, I've patched a 3 in there. See? Yeah, that's how to make an external. So I could also, let's say, I know that there's some code in there somewhere. I don't know where to find it. I could just do a search on the file and look for keywords, and it reports back, yeah, I found it. It's on line 1FO right there, you see. So there we go. So just cover a few things, additional things. That's basically the end of the lesson. But say I want to print out some line numbers. This will be useful a little later. We could be working in line numbers because sometimes when you're doing jumps, it's to the power of 16. So those line numbers can come in handy. And different ways to dump your value. Here's 16-bit values, 32-bit, and of course, let's say I got a hexadecimal value. I want to know what it is. I showed you some of this stuff earlier, but just a quick recap. There, I can print out whatever this value is here. If I want to convert a decimal to binary, like that. When using the printf command, you have to use this backslash. Otherwise, I could say, hang on, let me recall. This is not a big deal. It's just one thing works differently when calling echo. Then I don't need the command, the backslash. Yeah. But if I call printf and don't include the backslash when calling zero base, whatever, dumb little thing. Basically, almost all of these commands can be used interchangeably. Here, I could say echo instead of printf, and it'll print that to the screen. Same thing. It's just each of those echo and printf each have different parameters you can pass to them. If I want to convert a binary to text, whoops, I did that thing again. Control U. Yeah, convert binary value. Let's see. This one just dumps the first 64 bytes. 8 per line. Thank you. It's actually one line. Yeah. And this is nice if you're when you see the dots over here too. Like if this was hello world, you'd see hello over here. It prints any text that's in there in this segment here. There isn't any to print, but that can be convenient as well. Okay, so yeah, that's a pretty good tutorial. I hope I will go back and do some edits and preview and see where I made some obvious flubs. But thanks for tuning in.